So good evening, ladies and gentlemen. You've heard my name's Ian Phillips. I have a mixed heritage. I spent about 25 years in the mainstream oil and gas industry, taking all this stuff out of the ground. And then in 2007, myself and three colleagues set up a company, which was then called CO2 Deep Store. It morphed into something called Pale Blue Dot Energy, which more recently has morphed into something called Storega. And it's the company behind the Acorn CCS project based at St. Fergus. For my last 2 years with them, I was the project director for that project, so I have a reasonable knowledge of what happens in CCS. What I've prepared for you today is we can get the, a second, we just have to, there we go. Yep. So I'm going to do a very brief bit of background as to why we might even need CCS at all. I'm going to talk about the technology that works today and also how outrageously expensive it is. I'm going to talk a little bit about possible ways of capturing the carbon in the future. I'm getting one in business. And then I'm going to talk a little bit about doing carbon capture later, and even going to consider not doing carbon capture at all, but not producing the carbon. So a little bit of background. This is a plot of the world's energy consumption going back to the 1800s. The data comes from what used to be called the BP Statistical Review, now the Energy Institute's Statistical Review. And the key thing is that coal, oil, and gas, the hydrocarbons, the things that when we burn them create CO2, still create more than 80% of the world's energy. And probably even more depressing, the consumption of coal has risen very sharply, notably in Asia Pacific, which translates to China. And when you build a coal-fired power station, you're generally building something that's good for another 25, 30, maybe 40 years. So we've baked in an awful lot of carbon emissions. So the thing we're considering doing about it is carbon capture. And if you'll forgive me a little indulgence here, I'm going to use an analogy a couple of times tonight. I'm going to use an analogy with coffee. Coffee by itself is nice, tasty, but for some of us, caffeine's the problem. So we deal with the caffeine rather than getting rid of the coffee. And by a crude analogy, hydrocarbons works well for most people, but CO2 is a byproduct, which is clearly causing a problem, and we seek to deal with that. So the carbon capture process, I'm going to build this slide up, starts with wherever we consume oil, gas, or coal. So this might be in refineries, chemical plants, fertilizer works, cement works, and so on. And at present, we dump all that CO2 to the atmosphere, sometimes for free, sometimes there's a carbon tax, sometimes there's an emissions trading scheme price. And a couple of things to be aware of. The flue gas, that exhaust gas, is, depending on the nature of the process, between 3 and 15% CO2. So that means the other 97 down to whatever that is, 85% is not CO2. And the temperature is hot. It's come off a combustion process. So off the back end of a gas turbine, it might be 550 degrees C. Maybe at the top of a chimney, it might be as low as 150 degrees C. So what we do at present is capture that carbon using pretty much one technology, and that is a chemistry known as amine. Typically, we can get through a year, maybe between 90 and 95% capture. If the system's working well, it's 99 point something percent capture, but these things trip, they have imperfections. And the volumes we're capturing are big, between 250,000 and maybe 10 million tons of CO2 per annum. So this is a massive challenge. Assuming the plant works, we end up with CO2 coming off the end, pretty pure, and water saturated, which is quite crucial. Water is a problem with CO2. CO2 by itself not corrosive, but CO2 plus water makes carbonic acid, which rots steel very quickly. So we have to dehydrate it almost immediately, and we adjust any chemical composition depending on what was on the input side to clean it up. We also compress the CO2 for transport, lower pressures for shipping, higher pressures for pipelines. Those pipelines, which are good for long distance transport of CO2, might be in the range of 80 to 120 bar, which is typical for oil and gas type pipelines. So we know we can build them. Density is about 1,200 kilograms per cubic meter. If we ship the CO2, then we're either between -30 and -50 degrees C, and much lower pressures because of the amount of steel required to contain the pressure within a ship. And of course, if you're shipping, you have to build a facility at the port of departure, another facility at the port of destination. Assuming we've transported our CO2, it will generally go by pipeline to a store, so the same conditions in the pipeline. A typical storage well, we can inject in the order of 1 million to 1.5 million tons of CO2 each year, and we're injecting it deep underground into a storage reservoir. By deep, I mean 1 to 3 kilometers. It's probably the neatest place, the most convenient, the best place we have most knowledge about is a depleted gas reservoir, where we've taken mass out, so injecting CO2, relatively straightforward. You hear a lot about saline aquifers. There's much more storage, but they're full of water. So we need to, in many cases, remove water to inject CO2, or we need to find very, very big aquifers. So that's the basic process. The biggest challenge is this, the volume to be processed. So as I mentioned, CO2 typically 3 to 15% by volume in the exhaust gas. And if I take a gas-fired power station, 3 million tons of CO2 means I've got to process 100 million tons of hot contaminated exhaust gas to extract the CO2. And to give you a sort of sense of scale, I need to contact the CO2 in the exhaust gas with a liquid, a spray. And we need something of the order of magnitude the size of a big concrete cooling tower that we used to see at the old coal-fired power stations. Practically, we might end up with 4 or 6 or 10 smaller towers, but it's a huge undertaking to process this 100 million tons or so of fluid. Now, the technology is actually pretty well established. Amine is a commodity chemical. It's out of patent. It's cheap. And it's very flexible. We already have been using it for the last 50 to 70 years, extracting anything from 50% CO2 from a synthetic gas to down to 0.5% CO2 from a natural gas. But at the scale we're talking about, as you'll see in a moment, it is both capital and operating cost intensive. There are some newer amines which have been patented. Shell produced a thing they call Cansolv. Norwegian company Arca produced a new chemical, and a new start British company called Carbon Clean produced a new amine. These are, I would describe them as a bit better. They're a little bit less energy required to release the CO2 from the amine, but they're still horribly expensive. There's an emerging liquid-based technology. Leeds University spin-out they've developed a liquid solvent which needs much less energy to release the CO2. So that's offering some potential, but it's still fairly early stage in its development. Once you've captured it and compressed it, we need to transport it. So as I said, pipelines typically above 80 bar, density about 1,200 kilograms per cubic meter. We can ship at a variety of conditions. Low pressure and medium pressure are directly analogous to what we already do to transport liquefied petroleum gases around. So this is a modest amount of pressure, but very cold. There's a new concept kicking around, which is to transport the CO2 in vertical bottles inside a ship, sort of meter diameter, hemispherical ends, about 50 bar. And we could then inject that CO2 directly into a reservoir. So it offers the potential to reduce costs. But you'll see as we go down that list, the density goes down. So you need more ships to actually do the transporting compared to a pipeline. And to put it into context, 1 million tons a year at some coastal emitter in Europe, shipping to somewhere in the North Sea is probably about 50 cargoes on a decent sized ship, a ship by the way, which doesn't exist at the moment, but it's sort of potentially something doable transporting by ship. The CO2 process is very energy intensive. This is a phase diagram. You've got temperature across the bottom going from -80 up to +140, and you've got pressure in megapascals or bars on a logarithmic scale up the left-hand side. So the amine plant, the CO2 comes off hot, but fairly low pressure. In a pipeline, we need to be, as the CO2 needs to be liquefied in some way. So we're up either in a liquid state or a so-called supercritical state, which effectively is a liquid. So we're above that critical point. So we have to be both not too hot and quite high pressure. If we're shipping, we're down in this corner, lower temperatures, much lower temperatures, but much lower pressures. And that particular ship is one of the two ships that's been built for one of the early North Sea CCS projects, the Northern Lights project in Norway. And finally, oh yes, compressor has to do a lot of work to move the pressure up, so a lot of energy is required to do that. And finally, we're going to be storing deep underground up at quite high pressure, but quite high temperature. So to summarize amine as a concept, it's technically well established. We can capture using amines, we can transport by ship or pipeline, we can inject underground. And right now, the Global CCS Institute counts, there's 41 projects actually doing what I've just described. So capturing the CO2, compressing it, pumping it underground. There's another 350 or so in development. I take that with a very big pinch of salt. There's an awful lot of projects that have been in development and then disappeared. The crucial thing is that banks see this as proven technology. So if you're going to build one of these facilities, you're going to be spending hundreds of millions of pounds, and you're going to have to borrow money to do it. And banks take a very dim view of new technology. They don't like it because they see it as risky. So amine has one thing going in its favor, and that is that a bank will go for it. But it is horribly expensive to build. It is horribly energy intensive to operate. And by that, I mean an average estimate about $150 per ton of CO2 captured around the world, and the range, sort of the easier things to do, maybe $50, and the harder ones to do, maybe $250 per ton. And remember, we emit 38 billion tons of CO2 each year at present. It's also not very nice. It's caustic, toxic to humans, so we try not to release it into the atmosphere. And it introduced some exciting new hazards. So it's heavier than air, so if it leaks, it will displace the air, meaning it displaces the oxygen, so you die because you can't breathe. And if you happen to be unfortunate enough to stand next to a pipeline that's at high pressure and it leaks, instead of getting what the oil industry worries about, a jet fire, you get a jet refrigeration. You get very, very cold, minus 70 or so degrees C. So literally you would freeze to death very rapidly. So it adds to the excitement. Other ways in which we might capture that carbon dioxide is to do it differently. So there is a concept called oxyfuel, where you, instead of burning air with your hydrocarbon, you burn pure oxygen. As a result, you get pure CO2 as the exhaust, but the catch is you have to make a lot of oxygen, and that means freezing air down to minus 183 degrees C in very large quantities, very energy intensive. So I have to say I'm in the place of why would you bother? It's just as bad as doing conventional CCS. Another approach is to do pre-combustion capture. So in this, you gasify, which means cook at about 1,000 degrees C, gas or coal or oil or lignite. This actually breaks the hydrocarbon molecules down. So you end up with a mixture of 50% hydrogen and 50% CO2. And you can then bizarrely use an amine plant to separate those two. The hydrogen goes off to a gas turbine to make electricity, and the carbon dioxide can be compressed and stored as before. But again, it's so expensive, why would you bother? It's if you can find an alternative. And another particular issue with this approach is we've done it in a few places around the world where we've got lots of very low grade hydrocarbons, and they have very poor uptimes in the order of 60, 65%. So the technology not really working that well. So having told you we can do it, but it's not very pretty, there's a couple of alternative ways of capturing the carbon dioxide, which I'd just briefly like to review. Still in the why would you do it category is the idea of freezing the exhaust gas until CO2 drops out as a liquid, would happen at about minus 135 degrees C. It's a technique that we use when we're making all of those other chemicals above. We just literally freeze them out of the air. But we're talking about a lot of energy required to freeze these things, and just very, very expensive to do. Perhaps a little more likely, nanofiltration, so molecular scale sieves. These are ceramic tubes, a couple of meters long, about that diameter, and you can blow the exhaust gas up the middle, CO2 permeates out, so literally a sort of molecular scale sieve. The catch is that to capture CO2 from a big power station, you'll need a thing the size of an Amazon warehouse with literally millions of these tubes in. So a huge construction and huge maintenance challenge. Probably greater potential is something called MOFs, or metal oxide frameworks. Effectively, if you think of these as a metal foam, the little gaps there are in the size of sort of a couple of angstroms, and what you get is a huge surface area. The CO2 adsorbs onto the surface, and you then heat the metal oxide framework up, and it releases CO2. Technically, we know it works, but nobody's done it at any sort of really large scale. Oops, so maybe another possibility is to do carbon capture a bit later. And if you'll forgive me with the analogy, this is focus on capturing the carbon, but not worrying about when we capture it. So what you have behind that barrier across, or banner across the top is, oh, can we get rid of that? That's good. Okay. Thank you. So the one concept we could use is direct air capture, where literally we're sucking CO2 out of the air. Now, if you remember, I said natural gas was 3% concentration. We're down at 400 parts per million in the air. So we've got a huge chunk of technology required to capture this. And whoops. And it's frighteningly expensive. All of the technologies right now, over $1,000 a ton, with ambitions to get down to $300 a ton. So still not a very attractive thing to be doing. Another solution might be to use the carbon dioxide, and there's a lot of people very excited about a variety of approaches, making chemicals, making synthetic fuels, using it to feed microalgae to make products. You can even, in a few places in the world, go and buy precast concrete products that are cured in CO2 tanks so that they are a little bit stronger, and they've actually absorbed some CO2. And perhaps slightly more controversially, you can stick it in the ground and get more oil out from an enhanced oil recovery project. The problem with all of these is twofold. One is that CO2 is a very stable molecule, so we need a lot of energy to make these products. And the other is that the quantity of any of these products that we need in the world, even the most prolific thing we need, concrete, is about 2 billion tons a year. And when we're emitting 38 billion, this will be and we do this rather than a solution to our problems. Nature has rather helpfully been capturing carbon dioxide for many millennia, and there are a number of companies set up to do things like plant forests to absorb CO2, and to do things like wetland restoration, so that because wetlands and peat bogs absorb a lot of CO2. Commercially, they create credits, which they then sell to pay for doing this. And this nature-based approach actually has, I think, got some legs. One approach is to store a lot more CO2 in the ocean by enhancing the natural process. So on this diagram shows the natural equilibrium. We've got CO2 in the atmosphere from a variety of sources. The CO2 is absorbed into the oceans. It produces carbonic acid, which breaks down into hydrogen and bicarbonate. So bicarbonate is nature's way of storing the CO2 in the ocean. What's been happening recently is we've put more CO2 in the atmosphere, so the ocean has been absorbing more CO2, so we've been precipitating more bicarbonate. Helpful? So there is a company in Germany that has patented a process to accelerate this and do this in a scale of days rather than waiting for thousands of years. And their product, which they then dump in the ocean, is essentially mineral water. It's water with bicarbonate already in it. Big attraction is that it's also slightly alkaline, so as well as storing a lot of carbon, it slightly counters the acidification of the ocean, which has been going on. So these guys have patented the idea. They're a small startup, but to my mind, have got a huge potential. Another approach is to store or use seaweed, to farm seaweed to capture carbon dioxide. And most seaweed floats, it's got little air sacs. So this company has a little robot that squishes it all, pops all the air bubbles, and it sinks. So you have stored the CO2 in the plant life at the bottom of the ocean. I'm not sure what the longevity of that is, and I think that's one of the challenges with this particular approach. And we have a concept called enhanced rock weathering, where similar process to that in the ocean, we accelerate the natural process, rains through the atmosphere, absorbs CO2, lands on the land. mixes with calcium carbonate, produces carbonic acid, and it decays to bicarbonate, which is then just deposited in the water under the ground. Catches, again, a thing of scale. Somebody did a paper, which I'm not sure how much credence one would give it, but apparently if you took all of the agricultural land in the world and did this, we might be able to capture about 2.93 gigatons of CO2 per annum. So again, a contribution, but not necessarily a solution. And if you'll forgive me laboring this analogy, you could just decide to do something else completely. And my last couple of slides, if we just don't produce the carbon, the obvious thing is renewables. We know how that works. The price has come down spectacularly over the last few years to the point where solar is now the cheapest way to make electricity. And we have the potential to turn that electricity into hydrogen, of which there is quite a spectrum. The horrible stuff that is what we do today is either black or grey, where we're gasifying an existing hydrocarbon to make our hydrogen. Blue is what a lot of the oil industry hopes will happen, where you gasify the natural gas, but you then capture the carbon and bury it under CCS. But the holy grail is green, where you've got no emissions associated with it at all. Right now, it's economically more sensible to use your renewable electricity in the grid, which is what we do. But in the not too distant future, it would probably make sense to make hydrogen that way. Pink turquoise, I won't bother with. White is an interesting one. That's the color attributed to naturally occurring hydrogen. And right now there are some people drilling for that in the hope that they might find it and use oil and gas technology to produce hydrogen in large quantities. I don't know. So, ladies and gentlemen, that's my whistle-stop tour of carbon capture technologies. Sorry it took a minute or two longer, but hopefully you found that interesting.